Hey, very good afternoon. My name is Scheppingen. I'm Senior Database Engineer at MessageBird. Today, I'm going to tell you a little bit about a system of ours that basically is able to cope with the workload 95% of the time, but 5% of the time it gets overloaded, and not just a tiny bit overloaded, but we just get a torrent of workload sent to this database server. The immediate response would be something like, hey, can't we just solve this by sharding this? Yes, we could shard this database, and then we could have multiple shards performing the workload, and then it would be never overloaded at all, and we could easily scale out. However, it's not that simple to get from, let's say, a dedicated database cluster to sharding. There are problems for us integrating using, the application logic may not be completely aligned with sharding. And also our schema does not allow sharding that easily. So this requires a bit more work, more investigations on how we can solve our schema problems and align them with sharding. And shard them efficiently. You can only shard once, and once you're doing that, it's very difficult to change your sharding schema in a different way. There's a lot of debate on how you can fix this with very specific tools like with Vitess. With Vitess, you would be able to do other tricks to make it work. But let's not get into that today. Today, we're talking about what can you do prior to sharding. So how can we buy ourselves a few months of time, maybe a year of time, to build or rebuild our application and schema. So today's talk will be focused on that. Before I actually jump into the contents of the presentation, I first have to do a short disclaimer that my personal opinions in this presentation may not reflect those of MessageBird, but we're talking about the technical system here. So the technical system is owned by MessageBird. They're pretty much aligned. So today I'll talk about MessageBird, about me, give you context around the system, then tell you more about all the things we did to solve our own problems. But this is a journey. Your journey, in your case, may be different. It's more about how do you solve each and every problem and then find another problem to solve. And in the end, we reach a conclusion about one of the things, and that kind of surprised me myself, but let's not jump ahead of that. At the end, there is some room for questions. Obviously, if you have questions in between, just post them in the chat and I can have a look at them in the questions section. So first of all, MessageBird and me. Who am I? Well, I'm Scheppingen. I'm a database engineer. I've been in the MySQL ecosystem for 10, 15 years. I work for various companies that were scaling databases or automating databases, including several nines. I joined MessageBird about 2 years ago, or almost 2 years ago. And it's a very interesting company because they have very interesting problems to solve. So MessageBird itself is a communication company that has a platform that allows you to send messages, and you can send those messages via integrations or APIs, and you can send them over various channels like SMS, voice, Facebook Messenger, WhatsApp, Telegram. There are many of them that we try to integrate. And we also do acquisitions like 24 sessions that allow you to do encrypted video calls with, for instance, a bank. We also recently acquired SparkPost, that's an email platform, and we're also integrating that into our platform. And naturally, the company is growing through these acquisitions, but at the same time also on the MessageBird platform itself. So we are constantly seeking out for new employees. We have a work from anywhere policy that also allows you to easily work with us if you're not from Amsterdam or the Europe region. And that brings me to this slide. We're hiring, naturally. Have a look at the careers page. We're not looking at database engineers at the moment, but we're looking for good infrastructure engineers, developers, and all sorts of people that are in the engineering space. If you have any questions, also just drop me an email or send me a message and I can answer some questions for you. Right, let's get into our problematic database. So we have a problematic database, and what is the exact situation we started from? Like I said in the introduction, we have a workload that exceeds greatly the workload that it's normally doing. And that also means that it's behaving very different from the normal workload into this being hammered at the same time. And what I observed during, well, while fixing each and every step is that there is more to it than just one single problem. And that's only being amplified by the amount of traffic that we're getting. So during normal traffic, you won't see these problems, or you might observe these problems, but they're so small that you would hardly notice them. On a very high overview, this is how MessageBird works. We have our customers on the left. They interact with us via integrations or our dashboard API or our inbox, or at the bottom are APIs that allow you to integrate it programmatically into your backend systems, for instance. Today, we're going to talk about one of those APIs. Then we have the MessageBird platform to the right of that, and the platform allows you to send those messages via all sorts of channels, which are integrated into these phone carriers or being sent through the rich messaging systems like Telegram or Messenger. Like I said, we're talking today about an API, which is the batch API. And this batch API is meant to send out messages in bulk. And sending messages in bulk has low priority over other messages. So we deem these messages not to be important enough. We have high priority messages like, for instance, security codes and those kind of messages that need to be received immediately. So this is low priority and sent in bulk. So you can define a template message like you get 50% discount on Black Friday, and then send that off to many recipients at once. So you have one message being sent to many people. But you can also do that one-on-one. We don't stop you from using our API to do that. So you have a single message being sent to a single person. And with that, you can do a personalized message, but still send it on low priority. Now, what is the issue with this? Well, we saw prior to, I'm talking about 3 years ago, every API call to this system was a direct insert into the database. So what you get is a lot of parallel processes trying to insert these messages into the database. And as a customer is adding more and more workloads to that, or multiple customers is adding more and more workload to that, we get more and more parallelism happening in our database. So you get a lot of contention in the database. What normally people observe is, hey, we have a database that's not able to cope with our workload, and we're sending it too much traffic. Let's increase the number of CPUs on it. And yes, it will be able to handle all those threats, but it will not handle your contention. So more and more resources are fighting for the same single lock in your database, or the same single auto increment. So this is kind of counterintuitive for people, that you actually have to decrease the number of CPUs in the system to make it work better. And that's basically what we did quite recently. Then we have the issues of the one-to-n relation versus one-to-one relation. On a one-to-n relation, we have a single database insert for the template message. On the one-to-one, many inserts will happen, obviously. So they figured out a solution for this. Let's just stop inserting immediately into the database. Let's start queuing those messages. And that's a very good solution for the problem. I mean, I'm not saying that queuing messages should be the ultimate solution to this, but it's a very good way of decoupling your API from your database. So then we started queuing those messages and being able to handle them asynchronously. And that's also important. We have a low priority message sending, so handling them asynchronously is not really an issue. So the development team placed a queue in front of the database and a worker to retrieve everything from the queue and put that into the persistent storage. And since we're in Google Cloud, this is PubSub. Now, there is some problem after we added queuing, because first of all, we don't persist our messages immediately. And this is going to be a problem because if PubSub for some reason would have a major outage, we would just simply lose all messages that are still in PubSub. PubSub is multi-region, so it's not really an issue, but just in case. Other problem we have is that if we do not persist them immediately, there is latency between our customer inserting or adding them via the API and before they're persisted to the database. So we wish to get them as fast as possible from the queue into the database, and we do that by the workers, and we have multiple workers, but the more workers you add, the more parallelism you would create, and then you start getting into the same issue again. During high workload, queries are overloading the primary, and at the same time, there was no read-offloading happening on the replicas either. So the read requests were also hammering the database or hammering the primary. So there was a simple solution that I suggested we need to do read-offloading, and I was probably not the first person to suggest doing read-offloading. There were two API calls that would be extremely likely to be beneficial for read-offloading. That's the message status request. So that's basically what's the current status of the message that I sent, and then the customer status overviews. That's an overview for a customer with a certain selection criteria, like the last 100 or between 1st of February and 1st of March. Whatever status there is for that customer. So those are basically the overviews that we were able to offload. So we started offloading reads. Before I get into the finer details of that, I first want to make clear this service discovery picture. Jean-Francois and I presented this earlier today. Jean-Francois used to work for MessageBird. He designed the service discovery system. And what I want to say with this picture is that we are able to differentiate between writes and reads. On the left, we can see the writes happening via multi-layer proxy SQL setup, ending up on the primary. And then on the right, we are doing read offloading via replicas. And we can shape this any way we like. We could also include the primary, for instance, or add multiple new replicas. What we observed on those replicas once we started doing read offloading is that on the status requests, so the message status requests, we would get not only an increase in response times, but also an increase in the number of requests coming to the replica. So compared to the number of read requests happening on the primary, we got an amplification on the replicas. So where does this come from? Well, of course, we are replication lag prone. And since we are replication lag prone, we are doing a lot of inserts. Replication lag is inevitable. That also means that whatever we insert on the primary isn't immediately on the replicas. And that means that if a message status isn't there yet, it will automatically retry probably in a second or a few seconds later. And also customers are doing the same. They're bombarding us with requests for getting the status. So this is not good. We need to handle this in a different way. And then the team decided to do throttling. So we know we can handle about just a ballpark 1,500 messages per second. Let's just limit to 1,500 per second, and then we write 1,500 per second to the database. And Anything above that number, we will get replication lag, probably. Could be a little bit more, could be a little bit less. But this would at least get rid of the replication lag problem. But it's not a solution to the problem. It's only trying to solve the replicas of being overloaded. So a better solution was to start doing parallel replication. And you may wonder, why didn't you do that in the first place? Yeah, that would have been great if we would have had parallel replication from the start, but this database system was set up 4 years ago. And back in those days, mixed mode was still a default, and it was set up with the default. So first thing we need to change to enable parallel replication is having role-based replication, having GTIDs enabled, having, there are a lot of things that we needed to do first before we could even get to parallel replication. Another thing we need to wait for is the enablement of failover and switchover on our service discovery part, because prior to service discovery handled by what Jean-François and I presented earlier, is basically the application handling the failover. And that meant that there was a lot more logic in the application, and then it's much more difficult to do a consistent failover. So we wanted to be sure that everything went fine once we had service discovery enabled, and that enabled us to enable or change the parallel replication settings. Another thing that held us back from enabling parallel replication was we didn't do read-offloading anyway, so it was no use enabling parallel replication for a system that wasn't making use of that. So that's another reason. So once we were able to eliminate replication lag using parallel replication, we got the next question. We need to do a small delay for group commit. So basically what you do there is you add a tiny little bit of delay onto all the transactions. You tell MySQL just wait until X amount milliseconds or microseconds, and everything that you can then group together as one single commit, you can then execute that in parallel on the replicas. So then the question becomes, how much delay do you want to add? Because if we add a little bit of delay to our transactions, that also means that our application gets delayed. And then it gets basically latency added to every API call, which is also bad because then you get other issues like increased number of threads incoming. Also, we want to be very careful not to add too much delay because then you get also replication lag that becomes larger. So that was kind of an issue for us to solve. Also, what we learned is do not add this delay on a replica without parallel replication enabled, because you get into this, you get into endless replication delay. We were already near the capacity of that host for replicating on a single thread. If we do not have parallel replication enabled, that means that every transaction, the single thread that MySQL replication executes, also gets delayed. It gets an additional delay. It took me about 20 minutes to figure out what was happening here. And then I figured it out and then disabled the delay and everything was fine again. And the reason why I was doing that is because I started at the end of our topology while I should have started on the primary of the host and then work my way to the replicas. So we were able to add parallel replication. That was up and running, but how much do we need? How many threads do we need? How much delay do we need to add? And what we were doing here is basically trying to aim for the peak workloads instead of the normal workload. I can add, or I can tune these 8 threads very efficiently for our normal workload, but then during the peak times, that means that there is an incredible amount of delay happening on our peak workload. So I don't want to add too much delay to make our parallel replication efficient during normal workload. I only want it to be very efficient during peak workload. So we needed to be able to add a lot of workload to our system. And luckily, one of the developers already had created a small sysbench-like system that would insert a lot of messages into our queues that would just mimic our normal workload and never send out any messages. And then we found like 8 threads are working fine on our system, and we add something like 30 or 40 microseconds of delay. That doesn't sound like a whole lot, but during our peak times when we get like 1 million incoming messages, this is going to be quite efficient, and it's fetching just enough to satisfy the 8 threads of replication. So we also had another restriction that held us back, and we observed this during a huge influx of incoming messages. We already had parallel replication, but we still saw issues on the replicas, and you can see that here. These are basically the overview pages by our customers that are slow, and they're really slow compared to what they normally are. And the reason for this is because our schema was designed around a one-to-n relation. So we only used identifiers in our primary key. We had many indexes to make the overviews be very efficient. At the same time, all our messages have UUIDs. So these were pushing all these indexes out of memory. And I can show you an example table that looks a bit like what we're having. We're having a big-end identifier with an auto increment to make it as small as possible. We combine that with the created at date time to the primary key to allow partitioning per month. And then we also have our message ID, which is varchar 6036, which is a large object. And of course, this could be a binary 16 to make it more efficient. But in our case, we have it already there. And we have a unique index on this. And this is the exact problem we were facing. This is like a unique index that is large. This is a system that holds 4 terabytes of data. And then we have an index on customer created to make it very efficient to get an overview of our customer of the past 100 messages or between 1st of February and 1st of March, just as an example. So this index is needed for those overviews. So what we see during the peak workloads is that while we insert on the primary, new rows will be inserted sequentially, and that will follow the primary key. However, for each and every row, we have a unique UUID, which is random. And then, of course, you have a table of 4 terabytes. Having a random index that needs to insert something somewhere randomly inside that index needs a lot of this index in memory, and you never know where it is in memory. So these random inserts mean that this message ID index needs to be loaded almost completely. That means that there is less memory available to satisfy these range queries during peak workloads. The same actually also happens with the selects on the replicas, where we get requests to get the status of these messages, look up by message ID, which is also a random, and that also pushes the indexes out of memory. And there's a very simple solution to this: increase the memory. And it kind of surprised me that it was this simple. Our problem was actually very simple to solve. However, what did we do in the end? We scaled down at first to slow down our concurrency and added queuing. We started offloading queries to our replicas and then saw all sorts of replication lag issues, enabling us parallel replication, changing binary mode, tuning for our intensive workload. And then we needed to scale up again and increase our memory tremendously to keep all those indexes inside memory. And we might need to scale that in the future. But the results were there. The primary is still being hammered. We're still seeing a lot of issues on the primary happening. But on the replicas, it's doing fine. Of course, there's an increased workload during peak times. That's what you can observe, but it's not outrageously larger than what we're used to. So that's a very big a very big improvement. We can still improve a lot of things. We can still improve some scaling issues, scaling the weakest components. We can change our schemas. We can even diversify indexes by adding different indexes to different replicas, but that would only make it more difficult to do failover, switchover. We can also move some data out of our cluster, but that would require application overhaul to glue together large result sets. And that's not something we would be eager to do. While we could spend the same amount of effort on sharding our database and doing it properly. And that's also what basically our goal was: buy us more time to do it properly. That brings me to the final conclusion. We had a big dilemma. Do we need to optimize for the 95% of the time that was already doing perfectly fine, or do we optimize for 5% of the time that we apparently now made bearable for the upcoming months, year, and then fix it with sharding? And that's basically the message I wanted to bring, is that there is a lot more you can do prior to solving something via sharding. And that brings me to thanking you for attending, and we'll jump straight ahead into the questions section.